Okay, let us continue with the lectures, and today we will discuss about bandgap engineering. Bandgap engineering refers to, or it is also called sometimes as bandgap tailoring, bandgap tailoring. Refers to the various techniques which are employed to achieve bandgap modification. We have seen some of them. Some of the techniques which are used are, first we have already seen by alloying or use of alloy semiconductors. Use of alloy semiconductors. By alloying, taking different compositions, you can realize materials which have different band gaps. The second technique which is used is use of quantum well structures. Use of strain layer materials. These are sometimes referred to as pseudomorphic materials. Pseudomorphic materials. Pseudomorphic materials. We have been discussing about quantum wells in the last class. We will continue the discussion in this context of bandgap engineering or bandgap tailoring. Why do we need bandgap tailoring or bandgap engineering? Because we need to have materials with the different band gaps. For example, with respect to optical communication. Optical communication. In the context of optical communication, today we use Dwdm systems, which means dense wavelength division multiplexed systems. A large number of wavelengths in the low loss window of optical fiber. We use a large number of wavelengths in the low loss window of the optical fiber. So, those of you are not familiar, today's communication system, optical communication system uses WDM or DWDM system. So, if you see wavelength versus loss in dB per kilometer is a standard graph which we see. Fiber shows a low loss window. So, this is low loss window centered around 1550 nanometer. 1550 nanometer. The loss here is approximately 0.2 dB per kilometer. This loss here is 0.2 dB per kilometer. Silica fiber. What I have plotted is the attenuation spectrum of silica fiber, silica based SiO2 fibers, optical fibers, which are used for communication. So, in this low loss window, one can put large number of wavelengths in the vicinity here within this window. So, if you zoom this a little bit, then you can have around 1550, you can have large number of wavelengths. There are standard communication grid wavelengths. So, lambda 1, lambda 2, lambda 3, lambda 4 and so on. These are separated. The channel separation between these is typically, they depend on what is the channel separation which is used. In communication technology, the channel separation delta nu is, the standard ones are 100 gigahertz or 50 gigahertz So, corresponding to delta nu, you can calculate what is delta lambda, because mu is equal to c by lambda. Therefore, delta nu, this implies delta nu is equal to c divided by lambda square into delta lambda. So, around 1550 window, for every delta nu you can find out what is delta lambda with a negative sign, of course, which means 100 gigahertz spacing here corresponds to approximately, please verify this, 0.8 nanometer separation. So, in this low loss window around 1550 you can insert large number of wavelengths with a separation of approximately 0.8 nanometers in the same fiber, which means one fiber, so the optical fiber here carries all these wavelengths at the input. The advantage is every wavelength has a certain channel capacity and you have large number of channels. So, the wavelengths are very close, this 0.8 nanometer separation is quite close, and therefore, the word dense wavelength division multiplexing. Normally one uses WDM, wavelength division multiplexing, or frequency division multiplexing. Here it is, the additional D is to say dense wavelength division multiplexing, very closely spaced channels. To realize such a system, you also need sources, which is a laser which is used as an optical source. You need sources which are very closely spaced. One can realize these lasers using the same material system, but by going for band gap tailoring. A little bit of tailoring of the band gap can result in wavelength emission at very closely spaced lines. So, wavelength emissions which are very closely separated. So, you do not have to change the material system. For example, in communication one generally uses the indium gallium arsenide phosphide, on an indium phosphide substrate. So, this is gallium X, arsenic Y, indium 1 minus X and P 1 minus Y. So, this is the material system which is used to realize these lasers in the 1550 window. Using the same composition, it is possible by using the second or the third technique, exactly same value of X and Y, but using this second or third technique, it is possible to realize lasers which emit at slightly different wavelengths. Of course, by changing X and Y, that is the first technique which is allowing, we can anyhow achieve band gap modification. But even keeping X and Y constant, also it is possible to vary, and that is why the word band gap tailoring. How does this happen? We will discuss in detail. So, the need for band gap engineering or band gap tailoring is to realize sources or even detectors or certain devices with a specific wavelength response. We will discuss more about this at a later stage when we will discuss about the devices and tunable laser diodes. But at this stage, let us go into the technique. What are the techniques that are used? So, the first technique I do not discuss any further, because as we know, by changing the composition X of ternary compounds or by changing the composition X and Y of quaternary compounds, we can realize materials with different band gaps. Band gap is a function of the composition of the alloys. So, let us straight away go to second technique, that is use of quantum well structures. This will bring us in continuity with the last class on the discussion of quantum well structures. So, if we come back to the quantum well structure, if we take a finite quantum well, Finite quantum well refers to this finite barrier height potential V or V0. This is the quantum well. We have used notation L for the width and V is the well height. If you take a finite quantum well, as we saw in the last class, the energy eigenvalue equations are given by tan KL is equal to gamma by K. Or you can write this as tan inverse form. So, KL is equal to, where please recall that this K is K square is 2m by h cross square into E and gamma square was 2m by h cross square into V minus E. So, KL is equal to tan inverse gamma by kappa, gamma by K and plus m pi. If you want to get all solutions for a given L, you should first write it in this form, because tan is a multi-valued function, and if you write it in this form where m equal to 0, 1, 2, etc. For a given L, we are continuing the discussion of the last class, but in the context now of bandgap engineering, bandgap tailoring. For a given L, please see that gamma and K contain E. This will give energy eigenvalues, and therefore, for a given L, you can find out what is the energy eigenvalue. So, if you plot this as a function of well width L here, L versus E, that is, so if I have here E1, E2 and so on, depending on the width, it may support one solution or it may have several solutions. So, if you plot this value E, which I actually want to use the notation delta E, because E is the total energy here, axis. Now, this E1 is with respect to this, that is, this is 0. With respect to this, this is E1, and with respect to this, this is E2, and therefore, this is actually delta E1 and delta E2. This axis is our total energy E, which has EC, EV and so on. So, this delta E here refers to the energy of the eigenstates. So, if you plot this, then you will get solutions like this. Let me first draw the graph and then you see whether you understand whether this is all right or not. So, this is asymptotically . So, what I have plotted is, this is for the first state E1, this is second state E2 and third state E3. Variation of E1 with the width of the well. If you have a small well, the width of the well is very small, then this may support only one solution. Just like those who have studied optical waveguides, if you take a single mode fiber, so this is N2, this is N1, you have only one solution, which is the N effective here. That is the N effective of the fundamental mode. If you have a wider core, then it can support the second mode, third mode, it becomes a multi-moded waveguide. Similarly, in quantum mechanics, if you have a well of certain width L, then depending on the value of L, it may support only one solution, and if the well width becomes larger, it may have many solutions. So, E1, E2, E3 and so on. So, what I have plotted is as the width increases, this comes down, this goes on dropping down E1, because from top a new solution will come E2, and similarly from top a new solution will come E3. That is what is happening. As L increases, E1 is coming down, this is the energy value. So, this is 0, this is delta E, and after some value of L, the second solution starts, and E2 varies like this. So, the point here is, if you look at, for example, this region, the numbers may be approximate numbers, maybe this is 50 angstrom, this is 100 angstrom, 150. Typical numbers for a semiconductor, say gallium arsenide, 200, 250. So, L in angstroms. So, what it means is, if from 0 to 80 angstrom, let us say this is 80 angstrom. I am just giving an example to illustrate the point, 80 angstrom. For all well widths from a small value up to 80 angstroms, there is only one allowed solution. There is only one E1, there is no E2, E3. If you cross this, then the second solution will come. So, what has been plotted is the variation of energy eigenvalues with the well width. So, depending on your well width, you will have different values for the E1. Let us focus for the time being that our well supports only one solution. Which well are we talking of? We are talking of a quantum well, which means we are looking at a double heterostructure in which the sandwiched layer, low band gap layer, has a very small, has a smaller band gap. So, this is, for example, gallium arsenide, and this is aluminum arsenide. So, ALX gallium arsenide. So, we are looking at this well, this is the quantum well, the potential energy well in the band structure or a band diagram, energy band diagram of a double heterostructure. When the dimension of the sandwiched layer becomes small, it is a quantum well. So, it is this well that I am drawing here. These are also called, interestingly, man-made quantum wells. This is man-made, this structure is made by man, you have made it. So, it is man-made quantum well. Particle in a potential box is a standard topic in quantum mechanics, and all MSc physics students have studied in great detail. And this existed for very long time. The particle in a box problem was basically an approximation to potential problems which one encountered. If you have an atom here, a positively charged atom, then as we have discussed in our first class, the potential energy varies like this, and we approximate this by a box to calculate the energy eigenvalues. It was an approximation, simplification, so that you have analytical solutions. Today, this is a real problem, and you have real particle in a box. This box is real now. It is no more an hypothetical approximation, because these structures are real heterostructures, hence the name man-made quantum wells. You can grow double heterostructures and you can realize quantum wells where the original results of particle in a box that which we used to study in quantum mechanics are almost directly applicable. So, we come back here that over this range, if I vary the width, energy eigenvalue changes, which means, come back to the well here, E1 is here, and similarly there is a well here, it is a barrier for electrons or well for holes, which also has energy eigenvalues, which I call E1 dash for the valence band. In the valence band, Also you have a potential well or potential barrier which also have discrete energy eigenvalues. The lowest allowed energy eigenvalue is E1. The highest energy eigenvalue for electrons or lowest energy for holes is E1 dash. Please see when we had, okay, I have to erase some things. Let me rub these. When we draw the energy band diagram, EV and EC for a bulk semiconductor, we understand that there are large number of allowed states here and it forms a band. Correspondingly, the EK diagram, if you see, then we have the conduction band and the valence band, EK diagram for the band. So these are equivalent. So this is E and K. There are large number of states here right from EC, and therefore the energy band gap EG, which is here, an electron which is sitting right at EC could come down and recombine with a hole which is sitting at EV, and the energy of the photon which is emitted will be equal to Eg equal to h nu. Now this is EC, please see, this is EC of gallium arsenide and this is EV of gallium arsenide, bulk. But there is no state there. First allowed electron state is here and first allowed hole state is here, that is the lowest energy hole state. So the electron can sit here, electron can occupy this state, and this can recombine with a hole which is sitting here, which means now effectively the band gap is this. It is not EC minus EV of the bulk, but the band gap is this effective band gap. So EG effective is equal to EC minus EV, that is the original EG, this, plus delta E1, that is E1 actually, which I call delta E. Let me remove this. So plus E1, if I call this as E1, then this is E1 plus E1 dash for the lower band. So this was EG. Now we have E1. Please see E1, this E1 is the difference E1, or maybe it would be preferable that I please correct this. It would be preferable that we write because we have used E1 for an energy of electron in the valence band and E2 for energy of electron in the conduction band, and therefore it would be preferable to use this delta E1, delta E2, delta E3, in which case this is delta E1, delta E2. Kindly make this correction so that, let me show this as delta E1 dash and delta E1. The delta referring to that this energy is with respect to the band edge here. So this is the effective band gap which is larger than Eg. So this is one point, that the effective band gap in quantum well structures is, let me draw that again, effective band gap in quantum well structure, if I have an energy level here and an energy level here, this is Eg effective. The interesting point is, if you change the width of the gap, width of the sandwiched layer, that is width of this well, if you change the width of the well, you are moving, let us say you are decreasing the width. So if you are decreasing the width, then energy, this is going higher. So this comes to the new place here, and this also goes to a new value, and therefore the effective band gap now has increased. So what have we got? we have tailored the band gap by simply changing the width of the quantum well or by width of the sandwiched layer. This is tailoring. Of course, one can change composition, but if you see, it is easier to say that, oh, we can change the composition, but when you really see the fabrication process of MBE or VPE or any one of the processes, it is very difficult to, you can change the composition, but it is very difficult to control the composition to the required value. But controlling the thickness of the layer is very easy, because in MBE technique, for example, today you can grow layer by layer, monolayer. So, you can control thicknesses to one monolayer. One monolayer is 3 to 5 angstrom thickness. So, that kind of precise control is available in fabrication, and therefore, by simply controlling the thickness, we can change the effective band gap. If you change the effective band gap, the emission wavelength from this source, when we realize a source using such structure, the emission wavelength also changes. So, band gap tailoring by use of quantum well structures. You can take some numbers, how much, what kind of change is this? Put some number and see. Let us see, let me take an example just to get a feel, how much can I tune really? How much, what is the amount that I can tune? See, the maximum tuning possible of E1 is this region, that is the width of the well. From bottom of the well, I can tune up to this, that is the maximum variation that you can get. Let us say you realize a quantum well with a material, let me take our familiar gallium arsenide and aluminum gallium arsenide. Let me put a composition, say 0.35, gallium 0.65 and arsenide. Gallium arsenide is 1.42 eV, 1.42, and aluminum gallium arsenide you can calculate 1.424 plus 1.247 into x, where x is 0.35. You can substitute the numbers. So, you will have Eg of aluminum gallium arsenide 0.35, gallium 0.65 arsenide equal to, you can calculate this. I have done a small calculation. You will see that this comes out to be 1.860, and therefore, delta Eg is the band gap difference between this and this. Delta Eg is 1.860 minus 1.424, which is 6, 3 and 4. 0.436 eV is the delta Eg. Okay, very quick estimation that how much you will be able to tune, what is the wavelength range over which you can tune. You will see that the number is really very big. You can tune over a relatively wide range for all from the practical point of view. There is something here. This was Eg of gallium arsenide and this is Eg of aluminum gallium arsenide. So, Eg1 and Eg2. Delta Eg is the difference, where how much will appear here and how much will appear here. What is the discontinuity that will be? The point is, I have shown that there is a discontinuity here and a discontinuity here. It could have been that these are aligned and only the discontinuity is here, but no. In practice, there is a discontinuity, band gap discontinuity here and here. This is called as delta EC discontinuity, and this discontinuity is called delta EV. This has been determined by experiments that this delta EC is approximately 65%, that is 0.65 times delta Eg, and delta Ev the discontinuity at the valence band here is about 35% of the total delta Eg, and this is 65%. In the early 80s, this number was 85 and 15, 85% delta Ec and 15, but subsequently advanced experiments have determined that this discontinuity is approximately 65% and 35%. Why this is a bigger issue.
So this is depending on this material, or
This, the question is whether this 65 and 35 is universal for all materials. No, it depends on the material system, but for most materials which are used in optoelectronics, it is approximately in this region. Sometimes you will see 33 and 67, people are using 33 and 67, 30 and 70, but it is around this value, but it depends on the material system.
and it's dependent on doping also. It will depend on
Dependence on doping, the question is whether it depends on doping also. The dependence on doping is much smaller. The primary dependence is on the material itself. So let us assume this number. So if you assume 65% and 35%, please see our delta Eg is here, then this discontinuity that we have, why we are interested in this discontinuity? Because that is the maximum change that you can get from here to here. This is delta Ec. The maximum variation of E1 can be from the bottom of the well up to the top of the well. So delta Ec is 65% of this. So you know delta Eg, so you can calculate what is delta Ec, you can calculate what is delta Ev. This is, I think, delta Ec is approximately, you can see some numbers, 0.29 Ev, and delta Ev is approximately 0.15 Ev. Approximate number, you can multiply and see. Therefore, the total band gap, total effective band gap can vary from 1.424 up to 1.860, the maximum variation possible. You can calculate the wavelength of emission, that is lambda g corresponding to 1.424. You can calculate, check what is the number. We know immediately 1.24 divided by 1.424 will give you, I think, approximately 0.88 micrometer. If you put for lambda g corresponding to 1.860, so this is 1.24 divided by 1.860, the number will be much smaller. So this will come out to be, how much will it come? 1.24 divided by 1.86, approximately 1/3, 2/3, approximately 2/3. If I drop this and this, it is 12 by 18, which is 2/3. So it is approximately 0.65. The point is, you can tune the emission from 880 nanometer to 650 nanometer, maximum tuning variation. But this is a, when I talked about optical communication window, we need wavelength to be varied by 0.8 nanometer, less than 1 nanometer is the variation that we are talking of. So therefore, tuning, that is changing the emission wavelength by controlling the thickness, is the easiest way, because compositions, the gas mixture, gas flow rates in the fabrication process are kept constant. Simply the thickness is controlled. In one case you may have some 50 angstrom, and then next time for the next layer you may take 55 angstrom, 60 angstrom. So you change the thickness by 5 angstroms and the emission wavelength will change. So this is band gap engineering or tailoring. It is tailoring, it is adjusting the dimension. So that's why the name tailoring, band gap tailoring by use of quantum wells. We will talk a little bit more about these when we come to quantum well lasers, the devices quantum well lasers and strained quantum well lasers. The third point, let me briefly talk about the third point, that is strained quantum well structures. These are the three important techniques which are used for band gap tailoring or band gap engineering. So, the third point is use of strained layers. In the last class, we talked about strained layer epitaxy, strained layers. When you introduce strain in a medium, so normally you have the EK diagram here. This is the band structure. In the presence of a strain, what strain are we talking of? At the interface, there could be compressive strain or tensile strain. Tensile strain is where it is elongated. In the compressive strain, it is compressed, and this is done automatically. The layer adjusts itself so that bonds are complete. When bonds are complete, the energy of the system is minimum. That is why it tries to do that. It tries to do even if the layer is thick, but it is not able to do, and then it leads to cracks in the system, in the cracks in the material. And therefore, if the layer of the semiconductor which is being grown is less than the critical thickness, then it is possible to grow strained epitaxial layers without any defects. Now, one of the important implications of this or consequences of this is change in, so due to strain, the band gap changes. First, the simple picture. So, the band gap could change, which means it could become larger or it could become small, depending on in a given system, in a given material system, if the strain is compressive, and then if the band gap becomes larger, then if the strain is tensile, then the band gap becomes smaller. So, by control of strain, how can you control strain? Strain can be controlled by choosing the lattice mismatch. So, you can choose, for example, indium gallium arsenide on gallium arsenide, let us say indium gallium arsenide. You could choose 0.2, 0.8 arsenide, or you could choose indium 0.8, gallium 0.2 arsenide on gallium arsenide. The critical thickness in this case, which one do you expect critical thickness to be more? Please see, gallium arsenide has 5.65 angstrom as the lattice constant. Indium arsenide has 5.87 as the lattice constant. Here only 0.2 fraction of gallium is replaced. Therefore, this will have a lattice constant closer to this. This will have a lattice constant closer to indium arsenide, means further from gallium arsenide. Indeed, if you put some numbers, you will see that DC, the critical thickness in this case, is about approximately 100 angstrom, approximate numbers of the order of 100 angstrom. And in this case, I am sorry, in this case DC, because so we expect it to be more or less. Critical thickness is expected to be less. So, DC is of the order of 40 angstrom because the mismatch is higher. So, one can put the numbers, and we have seen that you can calculate DC is equal to AS by 2 mod epsilon and C. So, by changing the composition, you can change the strain. By changing the strain, you can change the band gap. So, one can choose a proper combination to change the band gap. Now, you could also argue, if we want to change the composition, why go for strain? We could directly change the composition and change the band gap. Yes, strain induced changes have many other advantages. A little bit more complication, some amount of quantum mechanics has to be brought in here, but okay, let me very briefly introduce. The valence band in a semiconductor is more complicated. It is not simple. We have been always drawing a simple EK diagram in the valence band. The valence band is actually more complicated. It comprises of a light hole band, a heavy hole band, and a split off band. So, I am now making it a little bit more complicated, and a split off band. This is the heavy hole band, this is the light hole band, and this is split off band. The same EK diagram. All the while earlier while I was drawing the uppermost band, because the electrons will get first filled here, or the holes which are interacting will be the holes which are here, and therefore, it is this band which is most important in normal circumstances. But when you introduce strain, what happens in this material is, at k equal to 0, this is k, at k equal to 0, the degeneracy between light hole and heavy hole breaks, and the two bands separate out. Depending on the strain, it could be like this. So, it could take, so the light hole could come up and the heavy hole band could still remain there. Heavy hole band and the light hole band. Depending on the type of strain, whether it is tensile strain or compressive strain, you could have a picture which is like this. So, the light hole band is here, heavy hole band is here. I will tell you what is this heavy hole and light hole in a minute, but let me first talk about band gap tuning. So, you can see that the effective band gap has been tuned, and the holes which are now interacting with electrons are in this band, light hole band. The band gap has changed and the effective mass of holes MV has changed, because this band is varying rapidly. So, if you find out, for example, for gallium arsenide, we know that MC is equal to 0.067 M0, and maybe I have given you what is MV was 0.45 M0. The light hole has a mass, MV of light hole is approximately 0.082 times M0. It is light compared to this. First point, heavy hole, it is heavy in mass, this is light. This is very simple level of talking, light, but basically it is because of the band variation here. So, now the carriers which are participating are electrons here and holes in the light hole band. In my original diagram here, it is the holes which have energy because they are coming first. So, they are the ones which were interacting with this. Now, it is this. So, the property of the semiconductor changes very much. This has certain implications, later we will discuss in realizing ultra low threshold semiconductor lasers. We will bring those complications a little later. For the time being, in this context, the band gap has changed and the effective mass of the carriers have changed by strain. If you had, let us say for example, this is compressive strain. if you use tensile strain, the opposite will happen. That is, this remains here, this changes a little bit, and the degeneracy is broken, but, and of course forget the split off is quite deep. So now the light hole band is here and heavy hole band is here. So if you use tensile strength for the same material system, the band gap has increased. Here the effective band gap has decreased. So please remember that the purpose is not just to decrease or increase the band gap. There are additional benefits which will come because of the effective mass of holes. Instead of heavy holes, now light holes will be participating. This we will appreciate when we discuss about devices, because that has an implication on the movement of Fermi level under injection, and the movement of Fermi level under injection conditions determines the threshold. You will see this at a later stage, but for the time being, by use of strain, you have the band gap modification and a change in the carrier mass, effective mass of the carriers. Now we have a few more minutes. What are these light holes and heavy holes? Very quickly, but you may have to refer to some more basic books. If you take gallium arsenide, every time I take gallium arsenide, because one, it is most widely used material, reason number one. Reason number two is we become familiar with one particular material, so that for any other material you can always extend the arguments. We know that this has 4s2 4p1, gallium is 31 atomic number, and outer valence shell has 4s2 4p1. Arsenide, atomic number 33, has 4s2 4p3. S2 means spin, it has plus minus half spin. Please see, S2 means there can be 2 electrons. In P there are 3 shells. So the 3 electrons could be all like this, or it could be so the total spin in this case is 3/2, and in this case it is half. Plus minus is possible depending on whether all of them are down or all of them are up. This is the total spin, and the angular momentum J is given by L plus minus S. This is called LS coupling, L plus minus S. L is the orbital quantum number, S is the spin quantum number. L for S shells, L equal to 0, for P shells, L equal to 1. This is the value of spin. So L equal to 0 and L equal to 1. Therefore, the total quantum number here will become, you can take values. So 1 plus minus half the total spin, which means this can become 3/2 and half. The angular momentum can take values 3/2 and half very quickly, and therefore you have 3 combinations. Now please see, S can take values 3/2 and plus minus half, J can take 3/2 and half, and therefore we have combination of states which are S, which are J comma S. The states are represented by J comma S, which gives the combinations possible are 3/2 plus minus 3 by 2, 3 by 2 here, and plus minus 3 by 2, 3 by 2 plus minus half, and the last one is half comma plus minus half. The first number is j. J takes values 3 by 2 and half, 3 by 2 and half. S takes values plus minus 3 by 2 and plus minus half. So, the combinations which are possible are these. This is nothing but the heavy hole band. This corresponds to the light hole band, and this corresponds to the split off band. Those of you who are interested, you can read more about this, but I thought, because I have drawn them, what do they really represent? These represent the allowed quantum states of electron. So, depending on the quantum state of an electron, they may occupy this band or this band or this band. So, this is light hole and heavy hole. The concept of light hole and heavy hole is a quantum mechanical concept. Please refer to certain books if you wish to know more about this, but our objective has been to see the band gap variation due to strain, due to tailoring of quantum well structures, and due to composition. So, let me stop at this point. We have covered most of the material aspects. In the next class, we will discuss about p-n junctions. You have studied p-n junctions, but my interest will be to see heterostructure p-n junctions. How would be a p-n junction, or what is the energy band diagram of a heterostructure p-n junction? Because most of the devices that we will see are p-n heterostructures. It is not the simple p-n junction which we normally study in electronics. So, we will see how they are, because that has lot of implications in the final device characteristics.